Hello, hello, hello. Hello, 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 hello,
Hello, hello, hello, hello, hello, hello, hello. Hello, hello. Yeah, I think now I'm crystal clear. Hi, Saltil D. Great dude. D was a D was a good problem, but E was also a good one. What was the E problem? Let's see together. Yeah, me too. Okay, this one, right? This was actually, yeah, this was actually easy problem. It was easier than D, I think. D was, I think, that one A, B, C, and D. D was this one, right? D was actually, I think D was tougher than E. So if you folks have solved till D, I would recommend do try E and F. E was actually pretty standard, like not a standard problem, but yeah, it had a standard approach, purely logical problem. A, B, C, and C. I think yeah, D was actually a good problem. E was on the easier side. F was also on the easier side, and G was also easy. So yeah, all problems were easy, but yeah, D was I think I found the best problem for this contest was D. I found it pretty much interesting. I forgot to see that I implemented try, forgot to see constraint. Try for which question have you like? I'm not sure. I didn't use try for any problem. So okay, for this problem, Zor, you might have implemented try. I think if you implemented try, I I would say it was more of an overkill. You don't like the constraints were pretty low, right? Oh yeah, right. So implemented try, forgot to see constraint. Okay, you forgot to see that you could just brute force, it, right? No, actually, I'm in my pre-final year, third year. There is coding. Yeah. Is also just one more thing. Chat, is my voice crystal clear? Like, do I need to change my mic settings? Because last time I think my audio quality was bad. Could you please just confirm? Can anyone confirm it? Is my voice crystal clear? Okay. Thanks. Thanks a lot, guys. Thanks a lot, guys. So yeah, we are going to discuss all the problems. There were 7 problems in today's contest of Codeforces Division 4. So yeah, let's start one by one. So we'll start from the very first problem. I think this contest was on a easier side because yeah, it was like a typical Division 4. So my like the best problem I found was the D1. Think it was interesting. Rest all problems were like purely logical. So yeah, we didn't had that much implementation part in any problem. They were like short codes, and you just have to figure out what the logic was, like that typical kind of contest. So yeah, so let's start from the very first problem, and then we are going to discuss till the very end the G problem. Think yeah. Okay, guys. So how are we going to discuss the problem? First, we are going to read the problem and understand the problem itself. Okay, it's very important to understand the problem. And next, we'll see the constraints and basically get it more, understand the problem even deeper, right? And then we'll make observations and intuitions out of our understanding, and we'll use that observations and intuitions to solve the problem. And at last, we'll see my code for the problem, so you can get a hint how I approached it. Yeah. So should we start? D was easy using sieve. We can solve it easily. You used sieve for D. Okay, great. I did it differently. I think I used a different approach for it. How to reach people? I'm stuck at 900 to 1000. I would say like read till STL if you are using C++. Get like don't touch hard topics uh, and the DSA part yet. I would recommend and do more questions probably. I solved using odd number sequence. Yeah, exactly. Me too. Me too. Me too. I also did it with odd number sequences. Great. 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 Initially, I tried it like brute forcing and stuff, but yeah, odd number sequence worked. Right? Like the constraints are pretty low for D. It was 10 raised to power 4. At first, I printed 2 to the power I and then sieve. Okay. Oh, got it. Got it. Got it. Got it. GCD odd into odd plus 2. Yeah, exactly. I also use this. It's like similar kind of algorithm. D was my favorite problem. Believe me, guys. I like G was not that good, and F was also not that good. Like I found D problem was like interesting. It took more time. E was much easier than D. I believe E was just brute force. Like if you guys need hint, and F was like some observation and logic. G was pure logic. So I would say this contest was a good contest. It didn't had like a lot of implementation part. I really hate implementation, to be honest. C was implementation and looked at, yeah, exactly, dude. Just as I said, I don't like implementation part. Yeah, let's start. Let's start. How do you guys don't you see if a contest compete with the guys who use it, especially in the like I think yeah, the AI wars was still going for this contest too, I think. In the common standings, I found lot of gray coders today. I think they all have already like the system have banned them already. So yeah, anyways, let's start so we could conclude this. If you guys like have any problem or like have any doubt, you can just ping it out in the comments. Even if you have a better approach or an alternate approach, you can just ping it out in the comments, right? Yeah, let's start. Lead codes, tomorrow's lead codes, weekly PCT, probably me. Yeah, it's gonna be me for tomorrow's lead code. Yeah, yeah, I felt proud. Great, dude, great. Yeah, let's start. The very first problem, the problem A. Okay, We are given an integer x. Your task is to choose an integer y such that the value of minimum x comma y is maximized. Okay. If there are multiple valued values of y, you can output any of them. Okay, great. So we are given an integer x. This is given. And then we are told to return the minimum of x comma y. Right. And this x is already given. And this y we need to find out. Find, right. And we want this entire value to be maximum. Right. Like typical division 4 first problem, right? It's uh, pretty easy one. Also, let's see the constraints. The constraint is the title of the problem is the 67th integer problem. So the constraints are minus 67 to 67, right? And we are given 6767 test cases, right? So it, this was like pretty clear and on the easy side. So we have to return we want this value to be maximum, right? This we are already given. That means that for all values of y, we need the minimum of x comma y should be as greater as we want, right? So if in this equation x comma y, if we choose, we have three choices, right? We could choose x equal to y. We could choose we could choose y greater than x, and we could choose y less than x. If we choose less than x, then as we are taking the minimum value, this value would be taken. Right. If we take this value and this is less, we will get a less number, right? Lesser number. But if we take this, right, if y is greater than equal to x, right, we will always choose the minimum number. That minimum number would be x, right? So we always get the maximum possible answer. Answer can never be x plus 1, right? Because we need the minimum number. So we would want that our answer could be x, right? Because we know that the other number could be greater than or less than x. If other number is less than x, then for our minimum equation, that would be our answer. But that would be less than x. And we want this equation to be maximum, right? So we'll take a number which is greater than x or equal than x. Right. I took a number equal than y, equal than x, because it wouldn't matter because the least number would be x. So this is, let's also see the code. Although it's like pretty easy problem. Let's see it. Yeah. So I took the input and for our value of y, I choose that same number itself. Right. So that's what we did. The minimum number would be the minimum x comma y. I choose y equal to x. So the minimum number is basically the same. It's x. This is what we did. I hope that's clear. What's your college name? I'm from Triple IT Rachi, bro. Which college you are in? Triple IT Rachi. Yeah, dude, I'm young. I solved 5 problems in the contest. Great, dude. The sixth one was actually, yeah, it was good actually. N equal to 67, then print 67 else n plus 1. Yeah, it's fine. But you can choose the same number too, right? Count, see out x works lol. Yeah, it works, right? Just print n. Yeah, exactly. That's what I did. What's your name? My name is Devansh. N equal to 67, then I think we can print 68. Also, I can think we can print 60. It's no need, right? Because we have to just take the minimum number. If we take that number itself, it would solve. I'm going to your profile back 24. You solve till diff 2b. You have now you solve. You can now even after solving b can't even. I think yeah, I'll just practice hard, dude. Let's talk about it later on, right? IDK we should print 68. Can we print 68, dude? I think yeah, you can print 68 because no, you can't. You can't. We are given constraints for the y, right? You can't print 68. Yeah, exactly. The constraints are given, right? You cannot print 68, but you can print the x itself, right? It wouldn't matter. Let's move on. Let's move on. Yeah. The 67 6 dash 9 integer problem. Okay. You are given 7 integers. You must negate 6 out of 7 integers, that is, multiply them by -1. Over all possible ways to negate 6 out of 7 integers, find the maximum possible sum of A. Okay, got it. Let's discuss this problem now. So this is a B problem. So we are given 7 integers, right? Integers. And we are told we need to negate 6 of them, right? And what we need to find? Find maximum answer. Find maximum sum. This sum is our answer. This is what we need to find, right? So this is the problem. We are given 7 integers. We have to negate 6 of them, and then we have to find the sum. So again, this can easily be solved with greedy, right? Let's say we are given this A3, A4, A5, A6, right? Because we are starting from 0, these are 7 integers. The basic idea is we can negate 6 of them, right? We can negate this. Let's say its value is x, it would become, negation means we are just multiplying it by -1. So if it's x, it would become -x. So similarly, we have to do it for 6 integers, right? 6 out of the 7 integers. We have to negate them. And then we have to find the maximum sum. Then we are going to basically add all of them, and we have to find the maximum sum. This needs to be maximum. How can we do that? So again, it's like we can think greedily, right? If we are negating it, if its sum is positive, it's going to be negative, right? It's gonna basically reduce some part from our sum. And if it's negative, it's going to be positive. Again, we would always want, can I say this? We would always want the least number to be negative, number or integer to be negative, right? Can I say this again? Right, but let's say we have given 3 numbers. We want to make any one negative, for example. For this example, let's say. So we would always want the least number to be negative, right? We would always want, because this would cause the least loss. Again, let's say we are given this example, -5, -2, and let's say 7. We would always want the least number to be negative. This would turn +5. This would give us the maximum benefit, right? Because we need the final sum to be as maximum as possible, right? So what we could do is, what I did was algo, right? We could just sort and apply negation to first 6 elements, to first 6, right? Can we do this? If we apply negation to the first 6 elements and we sort it, right, we basically completed our, like, we wanted the max possible answer, we will get it, because we would always want the least number to be negative, right? And we are going to start, as we sort it by ascending order, we are going to start with the least number, right? So this was my algorithm, right? There is also an alternate approach. You guys have might have think we only have 7 integers, right? So we can check all possible options, right? As we know, we can negate 6 out of 7. We can always choose one integer, right? We can basically try for all possible combinations for each element, right? Let's say this, for this combination, this is positive, rest are negative. So we can basically loop it out, right? The constraints are pretty less, right? We have only have 7 integers. Let's also see the code for it. So yeah, only this part. Those who guys are not aware, above is my template. Just ignore the above part, right? This is what what is necessary and what we should be concerned of. So again, yeah, we sorted it, and for the last number, I add it to the sum. Otherwise, I add its negation to the sum, or I subtract that to the sum. Right? Initially, sum is 0, and then I'm going to print it. Hope that's clear. Hope that's clear. Yeah, I'm going to solve all the problems too. Sort this and then do exactly, dude. Exactly. 2 star max and minus sum. Okay. Yeah, this also works. Basically, this is the same thing what we did. In D, I do multiple prime numbers, but I didn't pass. In multiple prime numbers, like how did you implemented it? Maybe paste your code. I'll see why it fails. Yeah, you can paste it out. Anyone in the chat can see it, right? Let's move to D. Rest are easy questions. Yeah, let's actually do it fast, right? Let everyone learn. Bro, someone may start with div 4, right? Yeah, exactly. Exactly. We'll go step by step, and then we'll move forward to the D and then E, then F, right? Because someone would be in their initial year, or someone would just be like, it would be his first contest, right? Because division 4s are rare, right? Nowadays, there are a lot of division 2s, but yeah, like when I was in my first year, we would have a lot of division 4s and division 3 too. Division 2 were rare, like I guess. But yeah, let's actually move towards the third question. So yeah, this was the entire problem. Even like if you have any problem after the stream, you can just ping it out in the comments or reach out to me. I'll solve it, right? So yeah, the C problem, the 67th permutation problem. You are given an integer n. You must construct a permutation of 3n such that if you partition the permutation into n contiguous blocks with 3 elements, the sum of medians of these blocks are maximized. More formally, you must construct a permutation of length 3n such that the median of all the like contiguous blocks of size 3 is maximized if there are multiple possible p output any. Okay, got it. Right. So basically, let's start here. So we are told we need to print a permutation of size 3n, 3 star n or 3n, right? And we have to make sure of this constraint while printing it. The median or the sum of medians, right? Of all n blocks should be maximum. Okay, great, great, great. Let's see it. And each block, size of each block, this is the third point. Size of each block is equal to 3, right? So basically, we are given as, let's say we make some permutation, right? The size of we would be given this n, then we have to make a permutation of 1 to 3n, right? I hope everyone is aware of permutation. Permutation is basically uh, like for permutation of array, this array, there would be, let's say if we are taking permutation of 3n numbers, there should be 3n numbers, and everyone must be distinct, and we should cover each number from 1 to 3n. Okay, so I hope that's fine. And then, so basically we need to make this permutation, and permutation could be any rearrangement, right? Let's say if you are making permutation of 1 2 3, it could be 3 2 1 and 1 3 2 or whatever, right? So these are called permutations. Permutation of n equal to 3, right? It included all the numbers from 1 to 3, all are distinct, and there could be any arrangement of them, right? So what we need to do is we need to basically make a permutation, then divide it block by block. The size of each block is 3, okay? And there are total n blocks, or okay, so there are n blocks. And what we need to find is the sum of median of each block. right? This for this block there would be a median, let's say m1. For this block there would be a median, let's say m2. We need this m1 plus m2 equal to maximum. This is what we are told. Let's also see the constraints. N is less than equal to 10 raised to power 5, and the sum of 3n would be 3 into 10 raised to power 5. Okay, great. Got it. So n is less than equal to 10 raised to power 5. This is the fourth point. Okay, got it. So this is the thing that we are already given in the problem, right? So again, it's a straightforward problem. So where we just need to ensure that the sum of mediums is as maximum as possible. Let's actually take this example and understand this problem more deeply. So we are given 6 numbers, 4, 5, and 6. Let's say this was our permutation. We would form n blocks, right? Here n is equal to 2. That means the permutation would be 3 star n would be equal to 6. So we are making a permutation of length 6, and we are ensuring after making this permutation, we are dividing the permutation into n blocks, right? N here is 2. That means 2 blocks. And after dividing in it, we have to make sure their sum is maximum. Let's take for this permutation, what would be the sum? What is median? What is median? Median is the middle element, right? The middle element. Let's say, for example, we are given 1, 2, 3, 4, 5 after sorting. After sorting the array, the middle element is called the median. Let's say we are given 1, 2, 3, 4, 5. The middle element would be this one, right? And this would be a median. Here we are given that each block consists of 3 elements, right? So the middle element would be 1, 2, 3, the second element, right? Or the second greatest element for our problem, for this problem, because the blocks are of size 3. Again, got it. What would be the answer for this permutation? Here the median is 2. Here the median is 5. So here the answer is 7. So this is our one of our permutation where answer gives us 7. Let's actually move forward again. Second, let's say we were given this 4. Yeah, this would be our first block. This would be our second block. What would be its median? Its median would be what I told, the middle element after sorting. Sorting is very important. So the median here would be after sorting this array would be 1, 2, 6. This is the middle element, so it's 2. After sorting the array would be 3, 4, 5. The middle element is 4, so this is 4. 2 plus 4 is equal to 6. Would this be our answer? Here our final the sum of medians was 7, but here it's 6. So no, this is probably not our answer. So how can we derive it? Like how can we think of it? Again, let's use greedy here. Right, let's choose greedy. We would always want the maximum answer, right? The maximum median. We would also always want the maximum median. Yeah, right. We also have one thing that the least number would be ignored. Least and max in a block would be ignored. Always be ignored. Right. This is just an observation from the example we did, right? We know the least and maximum element in the block will always be ignored, and we know that we need the maximum median. How can we do it? We would be given n blocks, right? So can we do something like it? Each block would consist of a least number and a maximum number and a middle number. This is our median, right? So we need this number to be as maximum as we could, right? So we are basically going to fill for the entire permutation, right? So let's do this. Let's do this. We know the least number in a block should always be ignored. Let's start filling this. Let's say we were given n equal to 3. That means there would be 3 different blocks, right? Let's think in this way. there would be three different blocks. Yeah, right. There would be three different blocks. Each block, there would be three positions. Yeah, exactly. And we know this position should be least, right? Let's start filling with it. Let's start filling the least possible position first. Let's say we filled one here, we filled two here, we filled three here, right? We filled the least possible position. The numbers which is less than 1 are not available. The number which is less than 2 is already contains in the block number 1 here, right? We can do this. Now let's say if we did this, now what we could do is basically we could fill the middle element everywhere. So we could do 4, 5, 6, right? And then we could actually fill the third or the largest element, 7, 8, and 9, right? This the When we comprise of this would always result in the maximum possible answer, because we always choose the best possible answer we could do in our middle element. We have already filled the least element, right? But we have not filled the maximum element. But it wouldn't matter, because every time this block would we would sort this block, and it wouldn't matter. So if we have already filled the least possible number, we just have to fill these two numbers. So this permutation would always result in the best possible answer. So we could fill it in this way, right? Let's take for this, let's check for this problem. So let's say again we would given two blocks. Each block there would be three elements. We'll start by filling the least possible number first. Then we could fill as we want, right? We could do 3, 4, then we could do 5 and 6. Right. Oh, just one thing. Okay. Yeah. So basically we can fill this way, right? Let me do some changes. We could do 4, 5, then 6, 7, then 8, 9. Right. My bad actually. I forgot it was like a different problem. So yeah. Anyways, back to track. What we did, we filled the least possible number first for each block. Now it wouldn't matter, right? I could just fill 4, 5 here, then 6, 7. So we get the maximum possible number in the median, right? And then 8, 9. Because each median would need a number greater than it in the block, right? So we are just going to fill it in the casual way. I hope that's crystal clear. This is what we did here. We filled the least possible number first, 3, 4, and then we filled the rest of the numbers. Here the median is 3, here the median is 5, it is 8. And you could also check for all possible combination. This would be our like the largest possible answer. Yeah, let's actually see the code for it too. Right, but I hope you all guys got the intuition. First, we are filling the least possible number, and then we are just filling it. Right. So because each number, if it's the median, there must be a number greater than it, right? So we are just filling it here. Let's see for the problem 3. Yeah. So this, let me actually zoom it. We made an array V, right? Here I'm just filling it. I'm first filling all the like multiples of 3 that give modulo 1. All the numbers that give modulo 1 when we do modulo by 3, right? So this is how we filled it. Then later we are just going to fill. If we are checking if it's not already been filled, we are just filling it and then we are printing it. I hope that's clear. Any doubt, guys? How to do G? Yeah, we are going to just discuss it. It's just implementation. Yeah, right, dude. Div 4 problems are solvable. Yeah, right. Also, each block start with a smaller element, 1 and 2 larger numbers. So hence f equal to 1. We can start for each block f plus plus. Yeah, you can do this. It's the same thing, right? Because the least and the maximum number would be again discarded in the final sum, right? Great intuition, dude. Like you live by your name, mathematics mental. Great intuition. It's just implementation. How to do J? Yeah. If He will just copy paste in the previous. Why not? Let's actually start from here. I think here I left. Yeah. See out prime. This is I think for D, right? Div 4 is full of cheaters. Yeah, exactly, dude. Div 4 is full of cheaters. Even Div 2 and Div 3 too, right? Nowadays, it's like a lot of fun has been destroyed by the cheating and the LLMs, right? 1 to N is this. Yeah, you can do this. This works. Using left and right pointers. I think for this problem. Median of three numbers should be A plus B plus C minus maximum element minus minimum element. Yeah, this is the same thing, right? Why not F and G? All forms. Yeah, we are going to discuss F and G too, right? So your D. So yeah, let's start with the D problem now. Great name by the way, is coding. Yeah, I think I'm going to use this somewhere at least. Like it's a great name. Let's actually start with the D problem now. I hope this was crystal clear. And even if you have still have any doubts, you can always ping it to me in the comments or wherever you think it's suitable for you. Let's start with the D problem. Construct a sequence A containing an integer such that GCD of AI and AI plus 1 is distinct over all AI greater than equal to 1 and less than equal to n minus 1. It is guaranteed at least one sequence A exists. Okay, each again the constraints are pretty low, 10 raised to power 4. Let's see it. And the constraint and the sequence we are printing, all the numbers should be less than equal to 10 raised to power 18. Okay, great. Let's see it here. The D problem. First, we are given. We are given that an array A contains an integers, right? And what we need to do is basically ensure that the GCD for AI, AI plus 1, right? For all I, for all possible I, must be distinct. This part should be distinct, right? This is what we need to do. And the third thing, we just need to print this, right? This is what we are told. We need to print this array or this sequence. And third thing we are told is the constraints are pretty low. It's 1e4. Right. So we are given three things for each n, right? And even the sum of test cases is less than equal to and 10 n raised to power 10 raised to power 4. Sorry. So this is the entire question, right? Let's see some example. For let's say we are given n equal to 3. That means there would be three elements a0, a1, and a2. And we are told that GCD for every two consecutive or adjacent numbers must be distinct. So these two are adjacent. So what's its GCD? GCD would be a0, comma a1, right? This should not be equal to the GCD of this, and if there are, let's say, more elements than GCD of this. So it should not be equal to GCD of a1, comma a2. And here it should not be equal to GCD of a2, comma a3, right? So basically we are told that the GCDs for all two adjacent elements must be distinct, right? So there are plenty of approaches if we are thinking in this direction. Let me also pull my solution for D. D is a very good mathematical approach. Yeah, D was a good problem, right, guys? Yeah, let's start here. So we want the GCDs to be unequal, right? We want all the GCDs to be like different numbers, right? So what we could do initially, let's actually see some real example. Let's say n was 3. N was 3. We could do some brute force, right? Let's say we took first element as 1, then we took second element as 2, and then third element as 4. GCD of this is 1, GCD of these two are 2, right? And we got different GCDs, they are not equal, right? Similarly, let's say n was equal to 4. We could do something like let's say 8 here. So this would be 4 and this would be different. And we can do multiples of 2 again and again. We could do 16. Now this is 8. This is not equal. And we could go keep going. This was the first thought that came to my mind. But the problem here is we are doing 2 to the power I minus 1 or 2 to the power I think. I minus 1, right? For ith element, right? I minus 1 for each element, right? But the problem here is I could be as large as n, right? 10 raised to power 4. And 2 to the power 10 raised to power 4 is too great number, right? It's a really, really great number. Even long that we use, LL or long, right? And C++ can hold up to 2 raised to power 63 minus 1, I think, in positive numbers. So we cannot store this number definitely, right? So the brute force approach would be doing something like this. Or the best intuition you could do is let's define the GCDs. GCDs and then decide the numbers, right? We want that the GCDs to be unequal. So let's decide these GCDs. What could be the first GCD and then second and then third, right? So let's do it for n equal to 6, n equal to 3. Let's take the GCDs are like 1, 2, and 3, right? And dot. So we would want the first element and the second element should be divisible by 1, should contain 1 as a factor. And then first and the second element should be divisible by 2 and so on. And after ensuring this, its GCD would be 1, its GCD would be 2, and we will go on. Right? There's a problem with this approach, right? Just we are building our logic step by step. So this is the logic, right? We are going to choose for all possible GCDs from 1 to let's say whatever numbers we have. But the problem with this approach is, let's say we are doing this. Let's say initially all numbers would be 1. We would want these two to be divisible by 1. They are already divisible by 1. We would want these two to be divisible by 2. So if we want these two to be divisible by 2, we are going to multiply 2 here. So this would be 2, 2. Again, these 3 would be 1. We would want these two to be divisible by 3. Then we are going to multiply 3 on both sides. So this the array would become 3, 2, 6, 3, 1, 1. We want these two to be divisible by 4, right? So this would become 1, 2, 6, 4 into 3, 12. And 4 here, 1, 1. Again, this 2 and this 2. We want this 2 divisible by 5 and this by 6. And after doing this, our final array would be something like this. 20, 5 into 6, it would be 30. And this would be 6, right? As GCD would be 1, GCD would be 2, GCD would be 3, GCD would be 4. But here on, this GCD is 10. This is a problem, right? This is a problem. So this problem occurs when we choose GCD as natural numbers, right? From we start from 1 and we until whatever numbers, right? We until 60, for example. So this is the problem with it. So what can we do to basically save us from this? Like if you think you would know this would occur because we are going to multiply both elements here and then both elements here, right? So there might be possibility we are going to confront even numbers here, and we did this, we sorted this, but when we are doing here, we would all again require even number. You got it right. Here we wanted odd numbers, so we multiplied it by 5, both numbers, right? 5, 5. But we also wanted these to get a even number, and these two to be an even number. The even number here was 4, and here even number here was 6. So we multiply both by 4, we multiply both by 6, and we multiply both by an odd number which was equal to 5. But they both got an even numbers here. That means that their factor at least contains a 2. Right. In our case, 2, the number 2 was a factor for both numbers. So GCD would be 5 and 2. But this would be a problem. Like in this case, all the GCD are still different. But the problem here is when there are, let's say, more numbers and we make somewhere the GCD equal to 10. We'll make it, right? marking it as natural numbers, right? So the GCD is not 5, so this is a problem. The problem here is the even numbers, right? So even numbers are problem. So how are we going to deal with the even numbers? Okay, great. Can we do this instead of marking the even numbers? Let's start the odd numbers. Let's start with 3, then 5, then 7, dot, dot, dot. In this case, the even number problem that while making these two, uh, while making these two the GCD of their correspondence, we multiply both by an even number. Similarly, with these two also we multiply with even number. Then this even number is basically when we do GCD of these two numbers, the even number is also coming out, causing the GCD to be some value which is not our intended value, right? So what we could do is to solve this, let's take all the odd numbers and then do this, right? If we do this, the even number problem is solved. The even numbers were problem and then it would be solved, right? You can try it on your own. Let's say this are the numbers, then this 2 would be divisible by 3, this 2 would be 5, 7, 9 and 11. The best thing about the problem was we needed distinct numbers, right? So we could just actually brute force and check it if our answer could be, we could get our answer till 10 is to the 4 or not. This is how I checked. I made the algorithm, then I used a map or a dictionary and basically after making this, you must have noticed, right? For every number, we are going to multiply it by two odd numbers, right? So even for the max number, it would be something like 2 into n plus 1 or into 2 into n plus 3 or something like this, right? Not exactly this. This would be minus 1, I think, right? Or no, it is, if we are starting from 3 depends, but yeah, two odd numbers, something like this. This would be something like n square. Right. Why telling this? Because we are given this constraint that all the numbers should be less than equal to 10 raised to power 18. So yeah, this n square, n is 10 raised to power 4. So this would easily pass, right? N square into 4 or something, right? Even n to the power 4 would pass. So it's not a matter. So this constraint would pass. And as we are using odd numbers, this would also pass, right? So there are no HK. This is, I think, the best possible solution. Let's see my code. Here is my code. What I'm doing, this IK is the GCD that I want to set. So this is 2 into I plus 1. Again, for I equal to 1, this would be 2 into 1 plus 1, so equal to 3. So the GCD would be IK into, this is just some calculation to ensure that if the numbers like we only multiply it by a number to make it divisible by it, right? For example, let's say we have two numbers, one is 15 and let's say another one is 21. We want both numbers to be divisible by, let's say, 21, right? Now what we could do is we could multiply both numbers by 21, right? Or what we could do is just multiply the necessary number. That necessary number, how we would get it? We would get it by GCD of 15 comma 21. We'll get the common factors and we'll multiply 21 by it. And we are going to multiply this number instead of 21 to it, so that our final number x is divisible by 21. This is divisible by 21, right? And this GCD here is in 15 and 21, I think only 3 is common. So DCD would be 3, 21 divided by 3 would be 7. So we are going to do 15 into 7 to ensure that this final number would be divisible by 21. So this is what I'm doing. The calculation part here, multiplying the that index and the index just after it, and then printing it. I hope this was clear and super crystal clear. Some people I think used sieve here. Now, if you're getting good rank in contest, that means you're also beating some AI in terms of speed. Lol, because many use LLMs. Yeah, okay, yeah, exactly. So, got it. You use sieve here. We only get 60 values. I think you did that 2 into 2's power, right? That, yeah, again, that doesn't work for too many values. Okay, you did this. Okay, got it. This is general solution. Okay, great. Great chat, great. Let's move. Let's move towards the fifth problem, chat. This is actually pretty easy one. Believe me, guys, this was actually a good problem. Chat GBT, Grook, Cloud. Again, let's see this problem. The 67th XOR problem. So you are given an integer array initially containing non-negative integers, that means positive or zero. You can perform the following operation n minus 1 times. Okay. So we are given an integer array. What's the name of the array? A. Got it. And integers. And second thing we are given as we have to perform this operation n minus 1 times. We are given some operations that we could perform n minus 1 times. First, we select an index I out of all possible where I is less than equal to the size of A, right? And we make X equal to that AI. Okay, got it. Then we do AJ equal to AJ XOR X for all elements. So basically, for every element, its value would be the XOR of X for its value. And then we remove that element. Okay, got it. So what's the operation here? Take an element, then XOR it to all elements. Then third thing, remove that element. Right. So we are going to take some element and then we are going to XOR it to the all elements in the array. And then we are going to remove this element. This is the operation we have, and we can do n minus 1 operation. It can be shown that after n minus 1 operations, exactly one element remains as an array. Exactly, right? Because after each operation, we are going to remove that element. So if you do n minus 1 operations, so we are going to remove n minus 1 elements, and then would be, at last, there would be only a single element. So your task is to determine the maximum possible value of the final element if you perform the operations optimally. Okay, great. The most important thing here is the constraints. Believe me, guys, like when I read the problem, I was thinking a lot of things, but when I read the constraints, I got, okay, this is the easier one. So it's around 3000, right? It's like 3105, but yeah, around 3000. Let's use this symbol to be precise. So this is what we are given. We are given an integer. We are told to do some operations. And finally, we need last element maximum. As large or maximum. Let's see this with an example. Let's say we are given 1, 2, 3. Right. And we have to do n minus 1 operations. That is 3 minus 1 equal to 2 operations. Here n equal to 3. For obvious reasons, we have 3 elements. So we have to do 2 operations. Okay. Let's take this element first. So if we are taking this, what we are told, we have to take an element, we have to XOR it to all elements and then remove it. So we take it, we XOR it to all elements. So this would become 1 XOR 3. This would become 2 XOR 3. And this would become 3 XOR 3. Right. And then what we are going to do, I'm purposely writing it like this, right? I have a, like, you will know why I'm writing it like this. So basically we did this and then we removed this. So now we have these two elements, right? Now what we could do is we could choose any of them. We did operation number, this is operation number 1. And operation number 2, let's say we choose this. Then we did XOR of this to both elements. So this would be 1 XOR 3, XOR 2 XOR 3. And similarly, this would be 2 XOR 3 into XOR 2 XOR 3. So again, the second step is to remove this. So we'll remove this. And this would be our operation 2. And this would be a final answer. So it's 1 XOR 3, it's 2. 2 into 2, 0, it's 3. So 3. So this is a final answer. And we want this element to be as maximum as we can. Right. So we have to randomly choose some permutation and later decide what could be the best possible answer. Right. The intuition, the key intuition here is to solve the problem here is understand this. You did XOR to all the elements. Later on, if we do XOR of this, right, you would do XOR of this to all the elements. You did it with it. We would have this 3 here that we got from the first equation, and this 3 here, right? And the XOR again, let's some XOR classes here. A XOR A is equal to 0, right? For the XOR problem, if 1 XOR 1 is equal to 0, 0 XOR 0 is equal to 0, and if they both are different, then we get 1, right? Right. So this is very important. If you are not aware of XOR, this is the entire manual. How are we going to deal with bits in XOR? So again, 3 XOR 3 would be equal to 0. So it would be finally 1 XOR 2. Right. This is a very important observation here because it's the only observation you need to basically solve the problem. Again, let me explain it like this. Let's say we had 4 elements. We choose this element. What we are going to do, we are going to XOR it for all the elements. This would be A XOR D, B XOR D, C XOR D, and D XOR D. And later we are going to remove this. Now, if we are going to take any element and we are going to do XOR of both for both elements, remaining elements. So it would be A XOR D, XOR C XOR D. Again, notice this. This T here that is in our element came from the very first operation. So this would be anyhow cancelled. So can I say this? Can I say this? That after first operation, I'm still doing, like, let's say if this first operation was not there, right? We only had 3 elements, A, B, C, and we directly removed this element. And I did operation now. So it would be A XOR C and B XOR C, right? Anyway, here too, this D would be cancelled out. So this would be A XOR D for first element. And again for B XOR D, XOR C XOR D, this D again would be cancel out, right? Because the like terms cancel out in XOR, right? So this two will cancel out. So this would be B XOR D. So again, B XOR C, sorry, here and here. So again, this is A XOR C, this is A XOR C, this is B XOR C, this is B XOR C. So can I say this? If we do an operation, the very second operation, the effect of this operation is null, no effects. Can I say this? This is a very important observation here. Right. The entire problem relies on this observation. If you notice this first, that after doing one operation, as XOR can, two similar XOR can negate each other. When we do the second operation, the first one nullifies. Right. Similarly, at last, what would happen is we would have, again, let's say we do this, we took this operation element, we do operation for all. So this would become A XOR C, B XOR C, XOR of both. Again, C would again nullify. So it would be A XOR B. So we, at last operation, what we did XOR of two numbers. XOR of two numbers. Hope you guys got it right. So like if you didn't got it, you can actually take a pen paper and try it on your own, right? If we are doing this XOR, right, after when we did this operation, it's fine. We got A XOR D, we took D and we did operation for all. Yeah, it's fine. But the second operation we will do, the effect of this D would nullify. This, the first operation would nullify, right? So we could say And for the very last element, it would be XOR of any two numbers. Right, the last number would be the XOR of any two numbers that are left out. Right. So we just want this value to be maximum. How can we find it? Can we just brute force it? Yes, we can, right? Because the constraints of n is, again, as I told you, like the constraints were very important for the problem. For n equal to 3000, we could easily do it for n square, right? We can easily find the answer for n square. So we could easily apply that and we could brute force the solution. So the final solution is we need the maximum possible XOR of two elements. Right. This entire problem has turned into the thing we need maximum XOR of two elements. Got it? So this is what we are doing in our problem. The implementation is a very easy part. I really love today's contest because of the implementation part. I really hate it and the implementations are pretty smooth and short for each the problem. So this is what we are doing. No, this is not right. It's the E problem, sorry. Again, ignore the template. Again, we are just doing two iterations to check the maximum possible XOR of any two numbers. This is what we are doing. And here we got our answer. I hope it's crystal clear. Anyway, can we do it linear logarithmic or linear arithmetic? Yes, we can. There is a data structure called trie. You can explore this out to do the similar thing. You can use this data structure, right? This can actually tell you for while we are iterating for each prefix, what is the best possible XOR you could get, right? For all the elements. This is where try is used. You can do this. You can try it. Check my doubt. But still, I have doubt that I've asked before. Since one element is XORed with every element except itself, at the end it will XOR with all the elements except itself. So the whole array XOR hua na. Please answer. Not actually. Again, this point. Here you notice something, right? What we did here. First, we did XOR of D for all the elements, right? And while we do XOR of this, XOR of this XOR of D has occurred twice, right? It became A XOR D into C XOR D for this element. And this D will negate, right? This D has been cancelled here. Here, this is our array. Do we have D in LE element? A's or D and C's or D, this is our array now. Do we have D here anywhere? No, right? D is missing here. Why is D missing? Because after this operation, it has been negated, right? This is the whole idea of the problem. I hope this is clear. I tries using try without realizing brute force was possible. Sadly, got it wrong. Yeah, exactly, dude. That D got cancelled, right? That D got cancelled here for every possible iteration. That's why. Yeah. This point is. By the way, nice name, watermelon with tomatoes. I don't know who eat watermelon with tomatoes. I think both are fruits, but yeah, again, let's not get distracted. But yeah, I know try, but clearly not good enough. Yeah, can study try in more depth because, like, that's actually a really good concept to know. Is answer max of all? Yeah, exactly. So this is n square. Yeah, exactly. It's not. Is this just not just the max of two numbers? Yeah, exactly. Can you take example of 67, 67 and try third one, please? What was 67, 67? This one. The XOR of max two numbers would be this two, and this would be. I hope it's all clear, crystal clear. Let's move forward. Let's move forward. Chat. Thanks, dude. Thanks. What will be rating of C, D, and E? I think the rating of E should be similar to D. Not sure though, like around 1000, 1100 to 1200, I think, in this range. This was a good problem. This could be like 1300 or 1400. Similarly, this too. Like C is max 900. Yeah, somewhere around that range, right? Was not able to solve last two. Yeah, let's move forward to the last two problems, which are actually great one. Let's move forward. Yeah, I think yeah. Like even if you have doubts after the contest, you can ping me up or reach out to me. Right. I have ideas for the F problem. Yeah, you can share your ideas. We can discuss it. Right. Let's move forward. So for the F problem, it's like pretty small problem statement. You are given two integers x and y. F. Right. First thing, we are given two integers x and y. Your task is to construct a tree with x plus y nodes rooted at node 1 such that there are exactly x nodes with even subtree size and y nodes with odd subtree size. If valid trees exist, you may output any of them. If no such valid tree, output no. Okay, got it. So we are given two integers x plus y, and we are told to form a tree consisting of x plus y nodes where x nodes have even subtree size and y have odd subtree size. Right. So this is the entire problem. Let's see the constraints. X plus y is less than equal to 2 into 10 raised to power 5. Typical O of n constraints. So these are our constraints. X plus y is less than equal to 2e5. That this is actually 2 into 10 raised to power 5, right? It's a short denotation for it. So this is what we are told, and we are need to find this tree. Right. Let's do step by step. So we have to find even sub x nodes with even subtree size and y with odd subtree size. What does this mean? What does this mean? Let's say this is our tree. And also one more thing, that our tree is rooted at 1. That means we'll always start the calculation. This is the parent for everything, right? This helps us to mark subtrees because this is 4 and this is 5. This would be a subtree here. And subtree size is the number of nodes in this subtree, right? For the number of nodes in this subtree is 3. That means it's an odd. It basically this node has an odd subtree size. And how many nodes we need of this odd subtree size? Y. Got it. So this is what we are told, that we need a node like a tree. For example, this element. Let me actually rub it. This is a beautiful 4. What is the subtree size? Is it even or odd? Is subtree size is it how many elements it has? It has 1. 1 is odd. So this is odd. What is its subtree size? It is also odd because it only has one element. It totally has 3 elements. It is also odd. This 2 is also odd. Right. What about this entire subtree? How many elements it has? It has 5. This is also odd. Right. For this case, it is all odd. But let's say for this 1 comma 2, 1 is our parent, so this tree would be something like 1, 2. What is the size of this subtree? 1, so this is odd. But for this, it's even. I think this is also one of the example, right? 1 comma 1. Let's take some example now. Let's take this 0 comma 3. What would be this? This would be 0 comma 5, right? X is equal to 0 and y equal to 5. Because we have no odd nodes or no odd numbers with subtree size odd, though no nodes with subtree size odd, and no nodes with subtree size even, and 5 nodes with subtree size even, odd, right? So this would x equal to 0 and y equal to 5. Similarly, we would be given this and we need to find this. And for this, x was equal to 1 and y equal to 1. This is the very first example, right? Where we need one subtree size as odd and one as even. So this is our array. Sorry, this is our tree. So what are observations here? What are observations here? One thing you must understand is for these two problems, the leaves are always odd. Leaves are always odd. Can I say this? Right. Now let's think in this direction. This is very good observation. We'll use it. Let's think. Let's think. What can we do? Let's first think maximum odd or maximum odd odd subtree nodes or maximum odd nodes. By odd nodes, I mean nodes with subtree size which are odd, right? Or the maximum y we could get for any, let's say, node, right? Always think in this direction. What are constraints of like what the maximum even number we could get or the maximum odd numbers we could get, right? We just made some observation here that the leaves are always odd, right? To get the maximum odd numbers, can I make a tree? Let's say for n equal to 5. Can I do this? This 3, 4, 5. This is a tree, right? Valid tree. So can I make a tree like this where we have one root and then all are just children? As all are leaves, all will be odd. And for this element, we would know if n is even. That means this would be even, right? Otherwise, if it's odd, n is odd, we would do plus 1 in our total number of odd nodes or total number of odd size subtrees, right? And the this would make us plus 0, but x would be equal to 1 here. Right. So the maximum number of odd nodes depend, it could be either n or it could be either n minus 1. Right. This is our second observation. Max odd nodes are either n or n minus 1. When it's n minus 1, when n is even. Because the final subtree would be consist of all, the final subtree would consist of all nodes, right? So that would be even, right? What is a subtree size? Subtree size is consist of all, it is the count of all the nodes that are present in the subtree. So right, so the maximum number of odd nodes would be either n or n minus 1. Okay, got it. This is our second observation. What would be the maximum even nodes? What would be the maximum number of even nodes? Let's think it. We need this resulted in the maximum number of odd nodes, right? For maximum even nodes, when does even nodes occur? Let's say we have this. This was even, right? So here entire tree was even. Otherwise, let's say we are in this. This would always be odd. This could be even, right? Whenever it would have one element only, this would be even, right? This would be even. So to for maximum number, can I do this? Let's say we need to find the maximum number of even nodes. Can I do this? I can just do 5, 6, and 7. Let's say for n equal to 7, right? An even node or the even subsize subtree would have at least one root, or sorry, at least one more node, right? For even subtree size, and we would always have at least one leaf, sorry, one node or one child. And the number of child should be odd, right? Because we want the total number of that subtree size to be even, right? So can we do something like this? For every node, let's use as least possible child as we can. And the as least possible child, we could use only one child for each node, right? And these all would be even, all even. And if n is even, we would do +1 in our total number of even elements. Otherwise, this would give us +0. So what would be the total number of elements here that we get? Or total number of even numbers we could get. It would be n by 2 always. Can I say this? Because each number would require a node, one more node inside it, right? For every number, for every even encounter we need to make, right? And the final encounter, if all the sum of, or if total number of nodes are even, then it would increment it. So our final answer would be n by 2, right? So these are two conditions that we have to make sure always, right? If the total number of maximum nodes would be n or n minus 1, right? When n is even, and the total number of maximum even nodes is this, right? Using this two, there is very good observation here. How you made the tree? You decided that if you want an even number, for every element you have a choice. If you want an even number, you can actually mark it here. Instead of starting it from its root, you can mark it, you can attach it to one of its existing child. Similarly, let's say for 5, instead of if we want it even, you can actually put it here, right? So we are using this strategy as well for our strategy. So first, attach all odds, then even, right? Because we just discovered it, if any subtree needs to be even, we need at least one leaf there, right? So if we need this element as, if we need, let's say, x is equal to 2, x is equal to 3, and y equal to 2. First, we'll find if it's possible, if it's possible. How are we going to find out? We are going to see if the maximum number of even and maximum number of, what are the maximum even numbers we could get from this tree? Here, n is equal to 5, right? X plus y. So maximum odd numbers we could get would be n, right? Because n is odd here. We already calculated it here. Maximum odd numbers is n when n is odd. N is odd. How we got it? We made a tree something like this. Okay, yeah, got it. So yeah, maximum possible odd number is n is equal to 5. So first we are going to check if y is less than equal to 5. Here y is equal to 2, so it's less than equal to 5. Yeah, this tree we can make. We also check if maximum number of even numbers are hampered or not. By the way, what are maximum number of even numbers? So this would be equal to n divided by 2. So this would be 5 divided by 2 is it's equal to 2. Let's check if x is less than equal to 2. X is 3. So no, it's not less than equal to 2. So this creates a problem here, right? We cannot create it. So similarly for each tree, first we'll check if max number of odd elements and max number of even elements we can satisfy or not. Now let's check for x equal to 2 and y equal to 3. That means we need nodes with odd subsize as 3 and even subsize, nodes with even subsize. We need total count of them as 2. Okay, great. Let's check again. The max odd here was 5. Is y here is 3. Y equal to 3 is less than equal to 5. Okay, this is great. Maximum even count is 2. And here x is equal to 2 and it's less than equal to 2. So yeah, that this works. Okay, yeah. This tree can be made. How are we going to make it? We know this n is odd. We'll always start with odd numbers. Always start with y. First, this entire tree is going to be odd, right? So we'll first start with 2. As entire tree is going to be odd, we'll subtract it. Y equal to 2. We'll do it 2 because now we need only 2 more elements as odd. So we'll make 2 and then we'll make 3. So these both are odd. Now now we need 2 even numbers. What we are doing? First we are filling all the odd numbers, all the odd nodes we need, and then all the even nodes. For the even nodes, now we need this element to be even. What we could do is we could attach it here. In this way, this would become odd and this would become even. After attaching nodes, we get the number of odd numbers we want. But now we need even numbers, right? So what we are doing is we are attaching this. Instead of attaching to this, we are attaching it to here. In this way, the number of even the subtree number of even subtree size count got incremented by 1. Even subtree size count will get incremented by +1, and this is going to basically go towards an even subtree, and this is how we could form a subtree with us, right? Got it. So this is what we need to find, right? So similarly for all x and y, first we make all the odd numbers, then even numbers. Just make of this case, if n is odd, we do y minus minus, because now the final tree would always be odd, right? And if n is even, we do x minus minus, and then we form the tree. And just also make sure while doing minus minus here and here, if here y is less than equal to 0 and x is less than equal to 0, due to this, right? This is also a no. We cannot make the tree. And if it's not, we can make the tree, right? And then how are we going to make the tree? Odd, attach odd nodes, odd number of nodes, or odd number of nodes are equal to y. Then attach x. Attach x nodes to existing one. Existing. Right. So this was the entire logic we have used. Right. Just for example, let me take this example again. For x equal to 2, y equal to 3. First, we checked if max even and max odd is all those constraints are well and good. Right. We have already checked it here. Let's check again actually. No issues. Max number of even numbers we would have is n divided by 2, which would be equal to 5 divided by 2, which would be equal to 2. Here, number of even nodes we need is 2. 2 is less than equal to 2. Yeah, it's fine. What about max number of odd nodes we could get? This would be equal to n because n is odd here. So this is equal to 5 and this 5 is less than equal to greater than equal to 3. So this also constraint. So yeah, this part is clear. Now we know n is odd. So what we do y minus minus because the final tree would be again odd, right? And we just put one element here. Now for every odd element, okay, for every odd element we attach to root. Why we attach to root? To make it leaf, right? To make it leaf. Leaf are always odd size subtree. So we just attach it. We attach two elements here. For every element, for every even element now, we attach to existing nodes. Existing. So we attach 3 here and 4 here. Now you can just calculate. This is an odd size subtree. This is an odd size subtree. But this would be an even size subtree. This would be an even size subtree. And this entirely is an odd size subtree. So we got x equal to 2 and y equal to 3. Right. So this is how we did it, right? Just also this part, when we do y minus minus, if y was initially 0, that means we needed no elements, no odd size subtree. But you know that as there are n elements and as there is tree, the size of subtree that starts with 1 would always be odd, right? It depends on the number n. So if this y goes less than 0, we are going to break and print no. Similarly, if any of these two conditions fail, we are going to print no. Right. Let's see my code now. Again, small code here. I calculated max number of odd nodes, max number of even nodes, then check if our condition satisfies here or not. If it doesn't, we are going to print no. Otherwise, if n% 2 is equal to 0, we are going to subtract it. If x is less than 0, we are going to print no. Right. And for number of even numbers, x is our number of even numbers. This is what we are doing for all odd numbers, 2 to whatever we have. I'm going to attach it to the root. Root is our 1. Otherwise, I'm going to attach this cn starts from wherever, start from the 2 already attached nodes. Basically, we attach this already attached nodes to our current nodes. Hope this implementation part is clear. Other than that, this logic is actually what like the best thing you should focus on rather than the implementation, because implementation may vary, right? But yeah, this logic remains the same. I hope that's crystal clear. Pokestar, thanks a lot, Pokestar. It really keeps it like, it really gives us the motivation to take these PCDs, dude. Did anyone find it much easier? Yeah, it was much easier. I'm in 2 years, I'm able to solve delay. Is it good growth or should I move better? Please tell guys. Yeah, it's if you are in second year, I think it's good, dude. Good. Whatever you think, whatever you like, find yourself, dude. I got W1 test scores. Exactly what I was thinking. I hope, like, I think you missed some part, I think. I was able to solve x equal to y while one node is connected to leaf node. Lamau. We combine subtree of same parity, reduce it 170, increase by one. All. If all nodes are considered of size 1, you have n. Got it. Optimal solution for D would be to use try data structure. D, sorry, for E you can try. D, I think, yeah, you can do sieve. I have not tried sieve myself, so I'm not sure if you can do it. But yeah, like chat is telling, so I think, yeah. Bro, at Monday, like, I'm a college student, dude. I'm a college student. So yeah, let's move towards the final problem, G. The 67th iteration of counting is fun. So yeah, let's do it. The final problem. Even after the PCD, if you have doubts, you can reach out to me. Okay, it's chill. So you are given two integers n and m, an array b of length n, such that it is guaranteed that every integer from 0 to m minus 1 appears in that array b at least once. Got it? So we have this array, right? Where every element from 0 to m minus 1 at least once, right? Occur at least once. At least once. Got it? And the second thing we are told is we are given two numbers n comma m. N is this its size. A group of n people are standing in a line in fixed positions numbered 1 to dot 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 n. They all want to sit down, but some are socially awkward to do so immediately. Okay, got it. For some arbitrary array A of length n, such that ai is less than equal to n and greater than equal to 0, each person I has a social awkwardness level of ai consider the setting process, which involves in discrete units of time 0, 1, 2 as follows. Okay, got it. So what we are told is we have n people, n peeps, and we are told that they all want to sit, right? But they are not sitting due to some social awkwardness. And each person I has a social awkwardness of AI, right? So this is fourth A array, which tells us social awkwardness for each person. Awkwardness. I okay, got it. And we are given some algorithm to find how they are going to sit. If AI is equal to 0, person I will sit down at time 0. Got it? Otherwise, if AI is greater than 0, the person I will sit down at the beginning of time unit t if both of the following conditions are satisfied. At least AI people have already sat down strictly before time t. At least one of their neighbors, person I minus 1, I plus 1, if they exist, has already sat down strictly before time t. Got it? So for sitting, we are given this algorithm, right? There were n people they wanted to sit, and we have told they will sit at some time t if these conditions follow. If AI equal to 0, they are going to sit immediately. Sit at time equal to 0. They are going to sit here. Otherwise, if AI is greater than 0, they are going to check two conditions. First, have already AI people sat or not? Like they have already sat down or not? And the second thing, if any adjacent have sat down or not. If they both agrees, we are going to make this guy sit. Right, this is what we are going to do. Yeah. Just 1 second, chat. Hello. Yeah, I'm back. So this is the question, guys, right? And what we are need to do at the beginning of every unit of time, each standing person check these conditions, what we are told, right? At beginning of time, at beginning of each unit time or each second, actually, right? We'll check this condition. All people whom the condition satisfies sit down simultaneously, and the process advances for next unit of time. For each value I, the given value bi denotes the time unit at which the person I sits down. Your task is to determine how many distinct arrays A are consistent with the given array B. Since this number can be very large, outcoded with modulo 676767677, right? That is actually very, yeah, this is this 67 some important number or what? Like they have used 67 in every problem. Like, does it have some historical significance or what? Like, I'm not sure. There might be, we could actually check it. I will check it out later, but yeah. So this is what we are told, right? We are given an array B, which tells us time ith element, ith person sat down, right? And we have to find all possible values of A. What is A again? A is this social awkwardness, right? Is the value which decides if a person is going to sit or not, right? Let's also see the constraints of the beautiful problem. So for the very beautiful problem, the constraint says m and n is less than equal to 2n to 10 raised to power 5. And we are told that what we are told? We are told that uh, sorry, yeah, this is what we need to find, and this is what okay. And also you have to do modulo this, right? For the answer. Just ensure it. That's an implementation part. Let's actually see some example. Let's see this example. Yeah. First, let's actually understand the problem again. So this B is some array, right? Where every element from 0 to m minus 1 exists at least once, right? And this B is actually this array which tells us where when each person sits down, right? When each person sits down, also bi is less than equal to minus 1, right? That means at m minus 1 second everyone sits down, right? This is the B, and we are told that there are n people who want to sit down. To sit, they will decide this. They are for each array A, where array A tells us about the social awkwardness, right? This array, we need to find all possible values of array A that will result in B. B is the time when they sat down. For and before starting of each time, they are going to check. Each person is going to check this condition. What is the condition? If AI or the social awkwardness value for that particular person is 0. If it's 0, they are going to sit immediately. All persons standing, right? The person who sats down, right? He's not going to check again and again. And if the person is greater, if the value of social awkwardness for that person is greater than 0, then he is going to check. If already AI people have sat down, this is the first condition he's going to check. Second condition, he's going to check if any adjacent they have sat down. After checking those two conditions, that guy will sit, right? So this is the entire problem. Now let's check this. Let's check that. This is our B. This means that this person and this person sat down at 0th time, right? They can sat down at 0th time only when AI is equal to 0. Can I say this? Right? We needed some A, right? We know that the for first and last element, this is going to be 0 because they can only sit down at 0th time, right? When AI is equal to 0, they are going to sit at T0. There are no other conditions, right? Because someone would be always standing. Initially, all are standing, right? We want if AI is greater than 0, we are going to check if the adjacent are at least anyone is already have sat down, right? So yeah, if AI, if 0 exists, this exists. Great. Now what about this? This person sat down at 1th time or the next second. We started with the second 0, 2 persons sat down. We started with the second 1, only one guy sat down. What would be the value here? A1, what could be its value? We know A1 would be greater than 0, right? Otherwise, it would have been already sat down, right? So yeah, A1 would be greater than 0. And we know this A1 would be less than equal to people already sat down, right? Why? Because we are given here, if AI is greater than 0, we need to check have already AI people slept, AI people sat or not, right? If that means this AI would be less than equal to 2. It cannot be 3 because if it's 3, he's not going to sit down because only 2 people have already sat, right? Also, we would have to check the adjacent person set or not. But I think this would already been covered. But if it's not covered, the total number of all possible arrays would be 0, right? Because adjacent has to be set, right? Adjacent should be settled down previously. And now we have to make sure of these two conditions. So it could be 1 or 2, right? Because AI is less than equal to 2 and greater than 0. So it could be 1 or it could be 2, right? And let's go for the next part. Next person, this person. This person has this. He sits down at the second. Again, for A2, it should be greater than 0. A2 should be less than equal to people sat, who sat, right? The people who sat are 3, right? Because this, and this, 3 people have already sat down, right? So A2 should be less than equal to 3. So can I say that this could be equal to 1, 2, or 3? But this could this be equal to 1? If this was equal to 1, he would have already sat down because his adjacent element has already sat down and the number of people who sat is already less than equal to 3. So yeah, it could not be equal to 1. It could not be equal to 3, but it could be 3. So all possible values, it has only one possible value. It has two possible values. It has one possible values. It has one possible values. We are going to multiply it because at last we want all possible values of A, right? All possible A's, right? So this would be 1 into 2 into 1 into 1. So this would be 2. So there is one clean observation. All are independent, right? Independent. This is a very important observation, right? Because if we got this observation, right, that all numbers or all people are independent, right, we can independently calculate the values of AI for that number. We can just multiply all possible values for all possible numbers and we could get our answer easily, right? Are they independent? Yes, because let's say it could be 1 or it could be 2. It would not disturb this element, right? It could be 1 and it could be 2, and this element or this person or this person or this element would not care for it, right? So this is the very important thing, that all are independent, right? This means all person can choose their values of AI or social awkwardness, and it would not affect others. This is a very important problem, right? This part was important. A second part, which I think many people neglected, was this adjacent slot. If you keep these two things clear, the answer was crystal clear. How we calculated for this array? We calculated all possible. If bi is equal to 0, if we see sats at 0th time, that means AI would definitely be 0. Then later we checked for this element that a1 should be less than equal to people who have already sat down. It would that is equal to 2. So it could be 1 or it could be 2. It could not never be 0. It has to be greater than 0, right? Because he has not sat down at the 0th second. And for this element 2, it should be less than equal to 3. But if it's 1, 2, as adjacent element is have already sat down, this creates a problem. Let me show you one more beautiful example. Let's take bi equal to 0, 0, 1, 2. What would be the corresponding AI? We would have 4 elements. We know these two would be again be 0 because they sat down, right? So we only have one choice for it, and you only have one choice for it. And by choice, why are we making choice here? Because all are independent. We would get choices for it when we could just multiply and get our answer. This is my final goal, right? If all people are independent, the values they could have are independent. We could just multiply all possible values for each element, right? So this would ensure that we could make all possible permutations, right? What do I mean? Let's actually show you some example. I'm going little off track, but yeah, this is very important. Let's say we had four people here, right? Here this could only be 0. Here this could be either 1 or 2. Here this could only be 3, and here this could only be 0, right? So we have one choice for it, which is 0. We have two choices for it, 1, 2. We have one choice for it, 3, and we have one choice for it. We would just multiply the total number of choices we have to get all possible combinations. How many choices we have here? 1. How many choices we have here? 2. How many choices we have here? 1 and 1. So all possible combinations would be equal to 2, right? Which would be 0, 1, 3, 0, 0, 1, 2, 0. And like how this visualization works, if you are not aware, like we will take this permutation someday, we'll take this permutation someday, right? So that's why we multiply, right? So this is how we can, you can think around this line. Like if you want to take feel of the problem. Let's move back to our problem. So here we are, we just need to find all possible options for each element, for each people. Now for this A1, right, we want to make sure that A1 should be greater than 0, A1 should be less than equal to people who sat. The people who already sat are less than equal to 2. So A1 could be equal to 1 and it could be equal to 2. Right. Also, we have to make sure that an adjacent is already sitting, or adjacent or the minimum of adjacent is the same thing. Minimum of adjacent is less than A1, right? So is less than B1, sorry, right? Or BI for each I, right? This is generally. For each element I, we are going to first make sure that this is greater than 0. Then this is greater than people who have already sat down. Then adjacent is already setting. This means that BI of the adjacent, the minimum value of the adjacent element, or minimum BI value of the adjacent element, uh, or the minimum of BI minus 1 or BI plus 1. It is the time they set out would be less than BI. Right. So this, if we take care of this case, we would know how many possible answers we could get. So we could get 1 or 2 here. But for this part, here it was 2, right? Let's check for this. This is not 1, right? This is 2, by the way. We only used it there, I think, right? Yeah. So A2, this. For A3, again, A3 should be greater than 0. A3 should be less than people who sat. And the people who sat are less than equal to 3. That means we have 3 possible values of A3, 1, 2, and 3. Second, we check if adjacent have already sat down or not, right? Or the minimum of adjacent are less than BI. Here BI is 2. The minimum of adjacent is 1. We only have one adjacent and it's less. So yeah, that's fine. So can we take all three values for it? Can we take it or not? This is the major problem here. Can we take all three values? The answer is yes. Why? Because no minimum element exists. No element have already, or no element already sits. Right. Understand, like for this part, this is the major part, right? Believe me, if you guys already know this, this is 80% of the problem itself. If you are checking this is 80% of the problem, or even 90% of the problem. Rest 20% is this part. Believe me, this was a really easy problem. How are we, why are we taking all three? Yeah, we can take all three problems here, all three here. So all 2 here. So the possible number of values for this are 2. Total possible values for this is 3. So this would be 2 into 3 or equal to 6. But what's different here? Here we could take all 3 values, but here we could only take 2 values here. In a previous example, let's understand it. In a previous example, it was 0, 1, 2, 0. Right. So we take two values here, one here, only one here and one here. But here 0, 0, 1, 2. These are the same numbers, by the way, just different permutation. 1 here, 1 here, again 2 here, and here we can take any 3 values. Why? Why can we take any 3 values? Because let's say we took it 1, right? This person would never sit, would never sit until its adjacent have sat down. This is a intuition behind it. So even if we took 1 air, we'll start from 0. These two will set, right? They sat at 0 times 0 and 0. Now F2 have set. If we have taken, we can take two values for it, 2 or 1. Either values they have already set and its adjacent have already set. This will sit at time 1. But this element, let's say if this was 1, if its value was 1, A3 was 1, it can still not set because its adjacent have not set, right? So even if we took one it and its adjacent is not set, it wouldn't matter. So this will set at time 1, right? After as its adjacent has set, it only required 1% to set. But as its adjacent have not already set, this can take all 3 values. 1, 2, or 3 wouldn't matter. And now it will set. Now it will set. Right. So similar algorithm, right? But just check this condition. Adjacent will sit just before all possible values, all positive values less than equal to all people set. Right. For this element. So basically using this, we iterate from the very first element and keep towards the last, go towards the last. And for all possible, we found all possible values for each AI and then we multiply them. So this was the problem. This was the entire intuition behind it. Right. Like I tried several approaches and also like it was unrated for me. I didn't try it out, but yeah, eventually I solved it, but with some time. But yeah, let's see the implementation for it. So here, just I'm inputting things. This code will be available to you. You can always check my Codeforces ID to basically check the code if you need it urgently. Otherwise, we'll ping it out in the comment section. So chill, guys. This here, I'm checking the frequency for all elements. This part is not needed actually. This part is actually needed actually. Let me tell you why. This FQ tells us how many elements will sat down before a particular number. Right. We always need this number, right? People who have sat down before. This people who have sat down before is calculated using FQ. Right. After calculating it, I'm taking this answer equal to -1 and Boolean. This is again like not relevant here. This is also not relevant. Only this part is relevant. Right. If the minimum or the adjacent of both numbers is equal to Vi -1. Right. That means they have just sat down. That means the answer is equal to all previous element into our answer. Otherwise, it would be equal to the frequency of its previous elements. Got it? For example, here for A2, as the minimum, let's take this example actually. Let's say it was like 0, 1, 4, and 3. We check for this, we have only one element. We check for this, we have only one element, one itself, right? If we check for this, we can add only one element because this will set, this will set, and we'll have only this three. Let's say we have two elements, then we could have two options here, right? One would be 3 and one would be 4, right? So this number of option here is frequency of frequency. In R code, it's defined by f of vi minus 1. How many elements of 3 exist, right? So how many elements of its previous element exist? How many frequency of its previous element, just previous element, or otherwise all possible people who have set down, right? And this case here, if minimum is greater than equal to that element, how when will it set, right? Let's say if we had this 4, 3, and 0, when would this guy set? If this guy sets, he needs one adjacent already set down, but they are going to set it after it, so it's not possible. And we are basically doing answer equal to 0 and we are breaking it, and finally we are just printing our answer. Hope this part is clear, right? This basically tells us that if all elements this part when we are trapped, right, adjacent will set just before, right? So all possible values, just one thing. Yeah, I hope it's clear. Yes bro, E is much easier. Yeah, E was easier. So we just had three parts here. Our very first intuition was if the minimum of both elements are greater, then we are going to break and we would have no options. Otherwise, if minimum is equal to vi minus 1, that means that any adjacent element would not sit until its own chance has come to sit, right? That's why we are going to put it that we are going to multiply it by the frequency of elements who have already sat down, and at last it would be the frequency of its previous element or the value just when we the value just below it, or when we do minus 1 by the value, right? And we again don't forget to do modulo to percent modulo after each multiplication operation, so we don't get overflows. And also in this question we had a different modulo, so yeah, we have to just switch it. So I hope the solution is clear, and if it's clear, do comment. Oh, like and share. See ya guys, I hope if you still have doubt you can actually ping it out in the comments section. Okay guys, see ya. Good night everyone. Thanks dude. Don't call me sir dude, I'm also a college student. You can call me by my name. I hope you guys don't have any doubts and it's crystal clear. So yeah, let's meet in tomorrow's lead code session, lead code weekly, and we'll carry forward the PCD. So yeah, see you guys then. Good night. Bye bye.